Hi class, we are on 13.9. This is having to do with freezing point depression and boiling point elevation, making water freeze colder or boil hotter. We live in Southern California. I've always lived in Southern California, so I've never understood salting a road. I'm sure some of you have been on the East Coast and in colder areas where this is common. So you will understand why people have to salt a road. But over here, that's completely foreign. And that has to do with colligative properties. Colligative properties are all the reason why you apply salt to an icy road, and that changes the melting point of the ice. It's decreased, and the ice will melt more quickly, making driving safer. If that doesn't make sense what I just say, don't worry, I have some pictures. So colligative properties is a fancy word, and all it does is mean that the properties which depend only on the number of particles of a solute in a solution, and we actually don't care about what the solute is. So remember, a solution is a solute and a solvent, and we do not care about what the solute that has been added to the solvent. We only care about how many particles have been added. Now, there is certain criteria for those solutes. So if they meet that criteria, we don't care about what they are, because what they want to do is either decrease the melting point or increase the boiling point. And if it does its job, then the rest doesn't matter in a sense. And I know that's crazy when we've been studying molarity and other things, but that's the whole point of this, is that we're not actually interested in what the solute is. But in fact, if you go into Chem 111 and we're back in person, you will probably do a lab where you'll do this. This will come back in 111 with molality. And you never know what the solute is, but you do the whole experiment. And you go through all the way to the end, but you don't know what it is. So let me get started on this. Colligative properties include a freezing point, boiling point, vapor pressure, osmotic pressure. These are certain things, but right now we're just going to look at decreasing a melting point. That's what we're interested in. So we want to take, for instance, a freezing point of water is 0 degrees. But what if we want to knock it down a few degrees to say negative 3.2? Then it has to get that much colder before everything freezes. So by keeping it at 0 degrees, we're not dealing with ice yet in our sidewalks. It has to still get down to negative 3.2 degrees in order for that to happen. That's what this is about. So colligative properties means adding a non-volatile solute. That means one that does not readily evaporate. So we want something that's not going to really go anywhere. It's going to stay in solution. It's going to intermingle with the solute particles. To a liquid, extend the temperature range over which a liquid remains a liquid. So the whole thing is just keep it from evaporating away, so that the liquid that we have added it to does not follow the typical behavior that it would. For instance, freezing at 0 degrees Celsius. The solution has a lower melting point and a higher boiling point than the regular liquid. And that's what these are called, the freezing point depression, where we now have knocked the freezing point of water from 0 degrees, added something to it, and now it's like negative 3.2. Water boils at 100 degrees, but what if we add something to it? Now it has to boil at maybe 103 degrees. So these little points, they may not sound like a lot, but if your car's overheating, that makes a big difference. So this is a nice little picture to show you. Remember, a solution is a solute and a solvent. So this would be normal. So let's say the normal freezing point for water is 0 degrees Celsius. But if we add something to it, we have now, see the blue, we have now lowered that. So the temperature has to go so much lower in order for things to start freezing. And the same thing goes for boiling. So if the normal boiling point is, let's say right here, if we add something that's non-volatile, now the boiling point has to get so much higher before it will actually start boiling. That's what this whole thing is about. That's what antifreeze comes in your car. Salting the roads. That's what these things are all about. So freezing point depression and boiling point elevation depend only on the number of solute particles in the solution. Why? Because the more particles that are there, the more they can block the water molecules from coming together. The attract is, it breaks the intermolecular forces, or the attractions from those coming together. So these are colligative properties, which depend on the number of dissolved particles and not necessarily the type of particles. So freezing point depression of a solution contains, again, a non-volatile solute to lower the freezing point of a pure solvent. So this is where we're going to use M, little m, and it's for molality. This is not molarity. Molarity is a capital M. This is molality, a small m, and the units are different. It is moles of solute over kilograms of solvent. And we're going to do a couple problems. So this is what we'll do. This means the number of moles of solute per kilogram of solvent. So again, moles over kilogram. So let's do a problem. Calculate the molality of a solution containing 17.2 grams of ethylene glycol dissolved in 0.500 kilograms of water. So now we're going to add this non-volatile solute to a solvent, and that's going to make a solution. And these particles, they don't vaporize away easily. We are now making a solution that's going to prevent the water boiling at 100 degrees Celsius. Okay, so here we go. We want the moles first. So this should look fairly simple and straightforward of getting from grams to moles. We're now going to, so that we have taken care of the top part of this equation. And we were given the kilograms of solvent already, and we're going to plug that in. And so what you see here, this line demonstrates where the sig figs are. We're going to plug that in, and the molality of this is 0.554 small m. That's the molality of this solution. All right, so calculate the molality of a sucrose solution containing 50.4 grams sucrose and 0.332 kilograms of water. Same thing. We're going to go through the same. This is another problem in your examples. It's not one that's worked out though, but it is. Let me see. It is problem. I'm trying to find it now. But anyways, this is a problem that's in 13.9, and here is, so we do the same thing. I cut out the part to determine what the moles are. Oh, this is Skill Builder 13.8. It's under example 13.8. And it gives us a molality of 0.443. So it's not very difficult. It's just different than what we've already learned how to do. Freezing point depression, it's the same thing. Where what happens is that these molecules, so if I didn't explain exactly what happens with the freezing point depression, and the same thing happens with the boiling point, is these particles block the water molecules from coming together, because once it hits a certain temperature, the water will start following the behavior it's meant to at that temperature, and that means coming together or melting. And what this will do, or freezing, is that the particles, if you see in this picture, see these yellow ones are all the non-volatile solutes, and they completely surround the water molecules, preventing the water molecules from coming together. Now the temperature has to go so much lower, and then once it gets to a certain temperature, well, the solute molecules are not strong enough to keep the water molecules apart. Then this will come together as a solid, or it will boil. So it will, for instance, it will block the way of the water molecules for as long as it can. That's what this is doing. So solvent molecules prevent solute molecules from forming a solid. It has to go way lower in temperature, not way lower, but a couple degrees temperature is still a big deal than what it is normally would be. It will not allow the solute to enter a solid structure, because the solute will prevent, the non-volatile solutes will prevent the water, for instance, the solvent, from coming together. This will lower the normal freezing point, and it's proportional to the amount of solute. So how many particles you have in there will make the change. It will be a big change or a small change. So this is why salt is added to icy streets. It makes the temperature lower for water to freeze. So if it's, say, 5 degrees Celsius, we'll just do Fahrenheit, 5 degrees Celsius, it has to get down so much lower in order to get to where it starts to freeze up on you. So when a solute is dissolved in a solvent, the solute gets in the way. So it's blocking the intermolecular bonds. The liquid can't form solid particles. This is pretty much all I've said. It's the same thing. Sugar water will freeze at a temperature below 0 degrees Celsius. The sugar gets in the way of the hydrogen bonds that water tries to form. The water molecules cannot form ice crystals until they are colder than 0 degrees Celsius. So that's exactly, it will block it and not allow it to happen. But then eventually it will get so cold that the water is stronger than the sugar and push the sugar molecules out of the way. Solutions that are ionic provide more moles, since ionic compounds fully dissociate. So what that means is that if you add sodium chloride, you've got a mole of sodium chloride, sodium ions, and a mole of chloride ions. So you've got 2 moles actually, and those are all in ionic form. So they're blocking the water from coming together. Compounds that do not dissociate still affect the physical properties of a solvent, but not to the same extent. So if you really want to block something, it's better to use something that's ionic, because you'll have more moles of it, because it'll dissociate, than something that will not dissociate, but will still do the same thing. So freezing point depression, this is now we're going to actually, I showed you how to do molality, but now we're going to actually look at how to do a problem. Okay, so now we're going to look at a freezing point depression. So we're actually going to plug in an equation to do problems, because what if you want to know what the final temperature will be once you've added solutes to a solution? So in this case, that's what the freezing point depression is. And this delta TF, that is the change in the freezing point temperature. KF is a constant for freezing point, and every solute has a different constant, so there's not one generic one. And then we have molality, which I already covered. So let's do a problem. Calculate the freezing point of 1.7 molality ethylene glycol solution. So we're given the molality and we need to find the freezing point depression. So the first thing we're going to do is you need to understand one thing here, that this is actually a problem that has to be done in two parts in a sense. Because what it's asking for here is the actual freezing point of the water. Now, water is normally freezes at 0 degrees, but this is going to be a different temperature. So we have to keep that in mind, that we know what water is. It's, it's 0. But what we're going to calculate is the difference of what the freezing point is. So that's what this page is showing, and I'll show you in a problem. So when you actually have to do the problem, it's 2 steps, not 1. So we plug in what we have. So we have M, and you see we have M here. We can always look up KF. I haven't shown it to you, but I'll show you on another table. KF is given. That's not something that you'll have to solve for. And that's what we end up here with certain units. You can see it's kind of Celsius kilograms over mole. The solvent and solute they added to clarify. And that tells us that we have a temperature of 3.2 degrees Celsius. But that's not the correct answer, because water freezes at 0 degrees. So we need to know what the difference is, what the actual temperature is by adding this amount of this solute. And by water is at 0 minus the new temperature, what's been calculated here, the change in temperature. And the freezing point will occur at negative 3.2 degrees Celsius. So that's what this is showing, how to set it up with the actual temperature. So this is done in 2 parts. Okay, so boiling point elevation, this is why we use antifreeze, because it helps with not letting our cars overheat, and that the particles prevent water from coming together. So this again is using a non-volatile solute, and it higher the boiling point. So for instance, water is 100 degrees. If we add something that's not volatile, it will have to force water to boil at a higher temperature. So antifreeze prevents not only the freezing of coolant, but it also prevents the boiling of an engine coolant in hot climates. And we're going to use something that's similar. So that the last one was an F. Now it's with a B for boiling. That's it. It's going through the same motions of what we just did with freezing. You just got to understand, are you looking at boiling or are you looking at freezing? So again, boiling, this is the change in boiling point in Celsius from the boiling point of the pure solvent. That's why we have to subtract. M is the molality, KB is a constant, and it's different for all solvents. And here is a table, not in your book, but I use this for another slide. I think I've mentioned I do 111 lab. And this is where you can see normal freezing point and normal boiling point. And then you can see the KB and the KF. So it's not going to give you anything more than that, because these equations are dependent on how much of the particles you're using. That will determine how big or small the boiling point or freezing point will change. So in this case, for this book, it gave us for 3 sig figs, but if you look here, it's giving it for 2 sig figs. So I'm going to go by this, but this is a table just to give you an idea of other things that are used. Okay, so calculate the boiling point of 1.7 molality of ethylene glycol solution. To solve this problem, we're going to have to substitute in the same way. So we are going to substitute in. We're going to look up the KB, gave it to us here. We're going to set it up, and we're going to get the change in the temperature of the boiling point, which is 0.87 degrees Celsius. So it doesn't seem like a lot, but it really does make a difference. And now, remember, 2 parts. We are adding this to what the normal pure solvent temperature would be. And so this increases it to 100.87 degrees Celsius. Where with the freezing, we subtracted it from the pure solvent because we needed to know how much lower it would be. But for boiling, we need to know how much higher it would be. And that's it.